And now that I've got your attention, we're not here to talk about wine, but about wine-colored zircon megacrysts from far north Queensland. These megacrysts are associated with sapphires. This work I did with Erica Porter and Mitch DeBruin at QUT, and I'm Charlotte Allen. Here's a map showing the distribution of sapphire fields in East Australia. They're associated with alkali basalts, and the lava plains field is indicated by the red arrow. These zircon megacrysts occur with the sapphires, and it's only the oddity of size and co-location that associates the two. There's no chemical evidence that directly links them. So we decided to look at aluminium. We investigated 3 color groups: Merlot, Rosé, and Champagne of these fingernail-sized zircons from Scot's camp. As an aside, the first time I dated megacryst zircons associated with sapphire was with Jackie Wong at UQ, and we dated 39 grains that gave a tight age of 13.6 million years from Weldborough in far northeast Tasmania. Jackie also put together the histogram showing the range of ages of both inclusions of zircon in sapphire and zircon megacrysts, that shows a range of ages between 300 and 200 million years and less than 80 million years. You can see that all of these alkali basalts localities are outside the 50 kilometer lithosphere boundary associated with areas where subduction has been active. The Scots camp locality is very close to this boundary, and using a new analytical setup, we decided we'd go in and have a look at these megacrysts, and we've uncovered a few interesting things. So the reference materials we use for zircon geochronology are relatively commonplace. Temora 2, the calibrating standards from an alkali gabbro from near the middle of New South Wales, and it's normal in size and catholuminescence. Plecevitza, on the other hand, is from a very odd rock, a hot alkaline granulite from the Czech Republic, and these zircons are millimeter to 2 millimeters in size. 91500 is from a single huge megacryst that resided in a drawer at Harvard University, originally coming from Ontario, and it's associated with some cyanitic rocks. The reference material we used for concentration was NIST 610, and we can also use NIST 610 to check to see how well we're doing our calibration for lead isotopes by looking at the 7:6 ratio. In this case, we measured 9086, which is very close to the known 9096, and this is a good result. I should also mention that for Plecevitza, we got an age that was somewhat too old, and for 91500, an age that was somewhat too young. Zircon, which is ZrSiO4, prefers 4+ ions, and hafnium, the sister element of zircon, is there at the weight percent level. Yttrium is the second most common trace element in many zircons, and it's there in thousands of ppms. It's a 3+ ion. The lanthanides usually have concentrations between 1s and 100s of ppm, depending on if it's a light or a heavy rare earth. Other elements do not fit well and are not expected in zircon, lead being foremost among them. But what about aluminium? It should not fit very well because of both its size and charge. However, Trail and co-workers through experiment have shown that zircons from strongly peraluminous melts have compositions, aluminium concentrations greater than 4 ppm, and marginally peraluminous ones and metaluminous ones well less than that. So here are the results of the 6 materials that we investigated in this analytical session, and those that were judged to be peraluminous are in yellow, which leaves only Temora as a metaluminous type. Champagne, Rosé, and Merlot all had aluminium concentrations well above that 4 ppm cutoff. I've also listed titanium here, and you can see Plecevitza is truly aluminium rich at 85 ppm. It also has very high titanium, and titanium concentration is a strong reflection of temperature. Plecevitza is a 850 degree granulite. You can see that Temora has a titanium concentration about 9.3, being a relatively normal igneous rock. You can see that Champagne, Merlot, and Rosé are all a bit lower than the 9.3 ppm titanium. So judging from aluminium contents, we would say all of these sources were aluminium rich except for tomorrow. Looking at zirconium, hafnium, or zirconium, hafnium versus uranium, we have a nice mixing trend on the zirconium, hafnium plot, with Merlot being at the high hafniums and Rosé being at the low hafnium concentrations. Chondrite value represents essentially the mantle. If you look at Bushveld, Hole rocks, and a bunch of other mafic rocks, you get results around 37 now for zirconium hafnium ratio. And somehow the crust or lithospheric processes managed to drive source rocks up in zirconium hafnium ratio, and this then is reflected in the zircon itself. This looks like a mixing trend, and I would argue that these very high values we see in Rosé at almost 90 and the very low hafnium contents are sort of our starting point for the system, and that the Merlot then is the more fractionated of the three color types. And compatible with this is being able to see that Merlot is also the uranium-rich zircon type with much higher uranium contents, which also makes it easier to date. Uranium being a very incompatible element in melt systems overall. I'll also mention that I've shown what the distribution of these concentrations are in a couple of different grains to show that it's not necessarily systematic in those Merlot grains labeled C, I, and R. And I've also labeled Champagne 1, a distinct cluster at about 55 zirconium hafnium ratio. So nature manages to produce a range of zirconium hafnium values. This is very large. These are some of the most outstanding zircons I've measured in terms of zirconium hafnium ratio. How does nature make such a source? Grimes et al. Came up with a classification diagram based on uranium, ytterbium, and hafnium, where more continental processes drive up uranium, ytterbium, and more fractionated zircons are driven to the right in having higher hafnium. And you can see our field for the lava plains megacrysts overlies his continental field quite well. In fact, it overlies his continental granitoid field almost in its entirety, except it extends to lower hafnium concentrations. These zircons are continental in character and not mantle-like. And on the right diagram, you can see the breakdown of the color types, with Champagne 1 off on its own compared to its mates, and two slightly different fields defined for Merlot and Rosé. So the Scots Camp megacrysts do not have a Morb-like signature and include some hafnium poor zircon types. Now on to ages. We mentioned Merlot grains were uranium rich and they were easy to date. 8 of 9 of them gave good ages. The one that failed gave a negative 207, 235 age. And this was the main reason that these 27 analyses would fail, would be having such low 207 measurements. So you can see in this case, we get a consistent age of 3 million years. Moving on to Champagne. Champagne 1, that individual grain gave a consistent age of 271 million years for all 3 analyses of that particular grain. And all of the rest of the Champagne, and in fact, all the rest of the Rosés gave these very young ages of 3 million years or less, many times failing to have a measurable 207-235 ratio. So summing up, we looked at sapphire-related megacrysts from lava plains from the Scots Camp locality, and the aluminium contents of those megacrysts indicate an aluminium-rich source. Aluminium content in zircon in general can be quite useful to measure. Zircon hafnium versus hafnium behavior of megacrysts needs to be explained, and at the Scots Camp locality, we measured 2 preserved ages, 271 and 3 million years. Thank you.